What we're going to talk about next, we're going to shift all the way from 1D systems to 3D systems. We're going to make a big jump. Ooh. And we're going to talk about a particle in a 3D box. The lucky part is we can utilize a lot of the stuff that we've learned about one-dimensional boxes and apply it to 3D. Now, have you guys talked about degeneracy of orbitals in any of your other classes? Like if you went to go draw electron configuration diagrams, just like that, these orbitals would be considered degenerate, right? You ever really thought about why these all have the same energy levels? Like what dictates that? Like for P's, how many per energy level, how many degenerate orbitals do you have for P's? 3? Yeah. Oh, that's for MOs. I'm just talking about AOs. But yeah, 3, right? What about for d orbitals? How many dashes would I need to draw? Okay, yep. F orbitals would be 7. Keep going. And then you'll learn those quantum numbers and stuff. But have you really ever thought about like why 3? Why 5? Or have you just been like, yep, it's 5 and moved on with my life? Yeah, yeah, I've just accepted. No, we're going to figure out why that's the case. And we can actually learn a lot from this three-dimensional system, even though it's pretty simple. So we're going to talk about particle in a 3D box. I'll try to share some cool visualization stuff that I'd like you to check out later too, so you can rotate and see these things in 3D, because otherwise trying to do it on here is not the easiest to do. Okay, so again, we want to consider a quantum system. Quantum particle. Contained a box of length A with B and height C. It has some mass m, and what we're going to say is the potential on the inside of the box. What do you think the potential on the inside of the box is going to be? Yep. Inside of the box is 0. Outside of the box what's the potential going to be equal to? One more big thing that we have to add based upon our last system. What do we have to say about the walls? The walls are impenetrable because, like we saw, even if there is an infinite potential, they can still move into those walls, which is nuts. So the walls cannot be penetrated. Okay, let's get up, or let's write down the generic Schrodinger equation and an applied Schrodinger equation for this system, and we'll be done for the day. So, whenever we start developing a quantum system, where do we always want to start? Yep. We want to look at the Schrodinger equation. We want to consider the generic Schrodinger equation. What's going to be the generic Schrodinger equation again? Yeah. Yep. H hat psi, E psi. What's H hat made up of? Yep. We got kinetic energy, and then we got potential energy operator. Okay. What do we know about the potential energy operator? Yep, it's 0 inside of the box. Outside of the box, what does the wave function have to be equal to? It has to be equal to 0 because it gets too big. Okay, so this will be 0 k hat. We have h bar squared 2m. How many dimensions do we have now? 3. Okay. With the 1D system, what did we have here? Yep, with respect to x, what do we need in this case? Yep, all of them. So y, and then finally z. Does anybody know another way to represent this? Have you seen it before? Delta? Upside down delta? That's known as a gradient. Okay. Next time, we'll apply this and we'll figure out, hey, now that we have 3 variables, can we separate these things out? And we can. There's a simple trick that'll show you guys to get around that. Okay?